Hi folks, Astronomy Live here. It's the moment of truth. Tonight I'll be reviewing the first results of my prediction made last night, where I predicted that the sun would be partially eclipsed by the Earth one final time last night from SDO's perspective, and that would be the final eclipse of this particular eclipse season. And again, it would be a partial eclipse, not a total eclipse. In the previous nights, it had been a total eclipse. In fact, it had been a total eclipse for the last few weeks. But last night, I predicted that it was only going to be a partial eclipse, based on data that I generated myself, calculating SDO's orbit using observations that I conducted with my own telescope and broadcast here on Astronomy Live on September 8th. So tonight I'm going to review the footage that SDO recorded last night, and conveniently enough, Steve Olson has uploaded a couple videos showing footage from that eclipse last night, which occurred as I predicted around 6:30 Universal Time, about 2:30 a.m. Eastern Time. And we're going to take a listen here to what he has to say in his video, but again, remember, I predicted this before it happened. I uploaded my video several hours before it occurred, when it was still September 12th Eastern Time, and predicted that within a few hours, on September 13th, at about 6:30 Universal Time, this partial eclipse would happen.
Things are weird, man, and we lose the sun mostly. What we have been doing is losing the sun every day.
He's talking about it being a total eclipse every day, that the sun was completely blacked out by the Earth every day, and it had been for several weeks. But as I predicted last night, you can already see it there. It just partially covers up the sun and then goes back out.
This is the motion that it takes. But the point is I made this little time lapse to show you in this little short amount of time, and this is only less than 20 minutes, guys. Something bops in front of the sun or discharges the sun and bops right the heck back out again.
He's saying it's a partial eclipse, that it doesn't completely cover the sun, and he's right. As I predicted, it was a partial solar eclipse.
Now, I want Ben and I want all these guys that have been scoffing at our channel to tell me what that is. And
Okay, well, I told you what it was before it even happened. I totally called that one. So it is the Earth passing in front of the sun as predicted. And we're going to take a very detailed look at the images that were collected by SDO, not just from the HelioViewer website. Again, remember one of my previous videos where I talked about the fact that these are high bit depth images that have been processed into low bit depth JPEGs on the HelioViewer website. But if you want the full dynamic range of the image, you have to go download the raw FITS file, which is available. Those FITS files are made available. So we'll go into that in just a little bit, but I want to show you the second video he uploaded as well. So quickly before I play this video, just to recap the second part of my prediction, which will be tested tonight, I said that there will not be another solar eclipse caused by the Earth passing in front of the sun from SDO's perspective tonight, September 14th. The eclipse that occurred last night, September 13th at 6:30 Universal Time, was the last one to cap off that eclipse season, and eclipse season is now over. So we'll go into a little more detail here in a bit about eclipse seasons and why they occur. I'll put that at the end of the video, but first let's take another listen to Steve Olson here.
Right at the screen, it does say that.
okay.
Yeah. Okay.
All right, so remember how much flack we're getting on SDO, even to and up to BP Earthwatch, I'll call you out, and SO, Suspicious Observers, and Astronomy Now, and all these different...
Okay, it's Astronomy Live. This is the second time I've had to correct this, but he's getting better. Originally, he called me astronomy.com, which, if you type that in, it takes you to the website for the astronomy magazine. But Astronomy Now, no, closer, but not quite. Astronomy Live. I don't know if he's deliberately getting my name wrong as some sort of tactic or to try to keep people from finding my channel and finding these videos explaining all of this, or maybe he's just got a memory issue, I don't know. But it's Astronomy Live, not Astronomy Now, not astronomy.com, Astronomy Live. It's two words. It's pretty simple, I think. Now, at the beginning of the video, they complain again about the double eclipse that occurred on September 1st, and the fact that the moon is sharply delineated because it doesn't have a significant atmosphere, and Earth is fuzzy because it does have a very significant atmosphere. And we're going to get into why Earth's atmosphere is significant here in a minute, but first let's just listen to their complaint.
Here's I think comes down to a couple simple points. Number one, we're told by the experts, NASA, the powers to be, that what we saw last week that we reported on was what they call a rare double eclipse, both the lunar transition across the sun and as well as the Earth. And we're told that the reason that there's two differences in how these eclipses look is that one is the moon that has no atmosphere, so it has a very clear delineation line. However, the Earth, that because the way it's passing in front of the Solar Dynamic Observatory satellite, that its atmosphere therefore gives a camera anomaly that makes it look unclean.
Yeah.
Okay, it's not a camera anomaly, it's just how the Earth looks at that magnification, because it does have an atmosphere, and so it's going to be fuzzy. It's not going to be a sharp edge. Alright, so let's play it here for another second.
That's BS.
Yeah. How is that possible?
Yeah, that's BS.
How is it possible? Earth has a much thicker atmosphere than the moon? I'm sorry, this is Astronomy 101. It's pretty simple, really. I mean, any amateur astronomer who's ever observed a lunar occultation of a bright star or planet has seen the fact that the moon doesn't have a significant atmosphere. It's just a sharp division, pretty much. It goes behind the moon, and you lose sight of the star or planet, and then it comes out the other side, and you regain sight of the star or planet without any noticeable disruption caused by any lunar atmosphere. You don't see any attenuation of the light, you don't see any refraction of the light. It's completely predictable in a geometric fashion. So, no, the moon doesn't have a significant atmosphere, but the Earth definitely does.
Absolutely impossible. So show us some pictures there, buddy.
Okay, I will. So, apparently this is Chris Potter. I'd never seen him before, but I guess he's been collaborating with WSO in the past, and I guess he claims to be a physicist or have contacts with a physicist, or maybe he knows a physicist, I don't know. But he claimed he's the one I think that's pushing a lot of this. The math is wrong, it can't possibly work. So we're going to test it based on the math. We're going to take a look at the images that were collected last night and compare it to my calculations, which will be based on the orbit that I personally computed for the SDO satellite using my own telescope and the images that were collected during the webcast on September 8th. So I've expanded the functionality of that spreadsheet, and I'm pretty excited to show you guys what it can do now, because we'll be able to directly compare it now to the images that were collected, and we're going to see, does it match up with the prediction? So Steve asked on my prediction video if I could tell him the source of my SDO data on its position. And if he'd watched the video, he would have seen that the data on SDO's position that I used in that video comes from my own observations, my telescope. And I replied to him with a comment stating that, but I haven't heard back from him since. I don't know if he saw the video and he just wanted to verify. Maybe that's it. Maybe he just wanted to verify what I said. And that is what I said, and it's true. I calculated the orbit of SDO myself. I guess that makes it inconvenient for him because he can't claim that, I don't know, NASA or the government is forging the orbital elements and trying to make it look like an Earth eclipse of the sun when it's really not, because the data comes from myself and my telescope, and I did a live webcast where everyone got to see the images being collected live, so there's really no opportunity for forgery there. Now, as far as the images from the SDO spacecraft, they keep using the images from the HelioViewer website, but as I've said time and time again, you should always go back and get the raw FITS files. So I'll include a link in the video description to the Virtual Solar Observatory, which is a repository for various observatories looking at the sun, including SDO. And you can go on there and you can search by date and time for the images you're seeking, and it will give them to you. And so I downloaded the raw FITS files for AIA 211. That's the 211 angstrom images that they showed in their videos back here. That's what these are. So it's the exact same images, but I downloaded the raw FITS files, and we're going to be working with that for the rest of the video. And I'm going to show you how it matches up with the spreadsheet that I created and showcased originally in the prediction video. And I've now expanded its functionality so that we can compare what that spreadsheet predicts to those actual images that were collected last night during that eclipse. So here are the images. I processed them with PixInsight from the raw FITS files into this animation, a time lapse, showing the partial solar eclipse occurring. You can see the Earth comes in and then it goes back out. And they seem to think that this motion is strange, abnormal, that it shouldn't have moved like that if it was really the Earth. So we're going to test that theory quite directly using the orbital information of SDO that I already calculated. So here once again is the spreadsheet that I created to calculate the apparent position of the Earth and the Sun from SDO. And I apologize for the clutter. I know it's a messy spreadsheet. I've actually used this spreadsheet for a variety of things, and it's been cannibalized and recannibalized because there are a lot of equations that go into this. All you have to do is put in the date and time, and it spits out all this wonderful information about the right ascension and declination of the Sun, the Earth, even now the Moon. I've expanded the functionality of the spreadsheet. It now computes the approximate apparent position of the Moon from SDO. If you give it the apparent size of the Sun in the image, the actual images from SDO in pixels, it will compute the image scale. If you give it the position of the Sun in that picture, it will tell you where the Earth is predicted to be relative to the Sun in pixels. So you can overlay a virtual Earth on top of the image and see whether it matches what was seen, whether there was supposed to be an eclipse, whether the motion of the eclipse matched what was predicted by the orbit. And so we're going to take a look at that in just a minute. So again, I apologize for the clutter. I know it's messy, but it gets the job done. Time constraints are tight here. Okay, I have to make these predictions quickly before the events actually occur. In fact, I might just run out of time. Here before my final prediction either comes true or doesn't come true. I'm recording this right now. It's about 12:50 a.m. Eastern Time, about 4:50 Universal Time. So I have very little time left before the final non-eclipse event either occurs or doesn't occur. In other words, the Sun will not be eclipsed by the Earth tonight, according to my predictions. So let's take a look here one more time at the double eclipse that occurred on September 1st. And we can see initially it was a total eclipse. The Sun was completely blocked by the Earth. The Moon was already in position, also in front of the Sun, but it was a partial eclipse caused by the Moon, but you couldn't see it at first because Earth was in the way. And then, once Earth started to get out of the way, it was a partial eclipse of the Earth in front of the Sun and the Moon at the same time. So the double eclipse is predicted. Again, this spreadsheet is using the orbit that I calculated for SDO to do its computations. It's not based on NASA data. So it does agree with what was seen. The timing information isn't quite as accurate as the official orbit because, again, I only made one night's worth of observations on September 8th, so the timing's not going to be perfect, but it's good enough to predict that there was supposed to be a double eclipse of the Earth and Sun at the same time. Now, if we go back to, let's go back to August 20th. This was when the first eclipse of this eclipse season, this recent eclipse season, was happening. It was a partial eclipse, and again, the orbit that I computed for SDO predicts it should have been going on for weeks. That's not a mystery. Finally, let's come back to last night and last night's eclipse. So we can use this information to overlay the predicted position of the Earth. It also gives us the apparent predicted radius of the Earth in pixels, and we can overlay that back on top of the images. Now there's one other factor we have to account for if we want anything close to an accurate prediction of how much of the sun should be covered by the Earth at any given time from SDO, and that is we have to account for Earth's atmosphere, because SDO is observing in extreme ultraviolet wavelengths, and the atmosphere is extremely opaque to extreme ultraviolet wavelengths. So we have to account for the additional size of the Earth brought on by the Earth's atmosphere. The Earth's atmosphere being opaque to those wavelengths will make the Earth look larger than it would if it didn't have an atmosphere. So not only is it fuzzy, but it's also expanded in radius by that atmosphere. How much? Well, we can take a look at data which has been around since before I was born and see just how opaque the atmosphere is at those wavelengths. So I'm totally dating myself here, but Skylab came and went before I was born. And you can see here a chart showing the opacity of the atmosphere at various altitudes at various wavelengths. Now keep in mind, SDO's wavelengths are given in angstroms, and these wavelengths are given in nanometers, and there are 10 angstroms in a nanometer. And so the wavelengths that SDO is observing at are similar to the lines you see up here at the top for the extreme UV images. That's most of the images you see coming from SDO. However, the 1600 and 1700 angstrom images, those are what we call far ultraviolet wavelengths. Those are not extreme ultraviolet wavelengths, and they're more akin to what you see down here in this region. And notice that the opacity of the atmosphere is much less for longer ultraviolet wavelengths. It's still far ultraviolet, and the atmosphere still does block it to a large extent, but you can see basically deeper into Earth's atmosphere at those wavelengths, which is why you see this big disparity in the amount of the sun that is eclipsed for any given time between the 16 and 1700 wavelength images versus all the others, all the EUV images that are at much shorter wavelengths of light. And so you can see here the atmosphere is basically completely opaque to these really short extreme ultraviolet wavelengths up into about 240 kilometers. That's big, and so you have to account for that factor, and that's what I've done with the spreadsheet. So you can see here, all cards on the table with the spreadsheet, we've got the polar radius of Earth, and the atmospheric height we just saw from that chart, 240 kilometers for the wavelengths that we're dealing with here, these extreme UV wavelengths. Now for the far UV wavelengths like the 1600 and the 1700 angstrom images, you can use a lower number for the atmosphere, and that will reflect the fact that you'll see it in the images. The Earth doesn't cover up as much of the sun at those wavelengths because the atmosphere isn't as opaque to as high an altitude at those wavelengths. The atmosphere is more transparent at those wavelengths. It's still very opaque, but not as severely as it is to extreme UV. You really need a hard vacuum for those extreme UV rays, which is why SDO is necessary in the first place. You can't just put an extreme UV telescope on top of a mountain and call it good. You're not going to be able to do the kind of observations that SDO does. That's why SDO is necessary. That's why SOHO, Stereo, these spacecraft are necessary to be able to observe the sun at these wavelengths. If there were an easier way to do it, that would be the first option taken. But if you're looking for extreme UV wavelengths, you're going to find them coming from spacecraft like SDO for that very reason. So finally, what I did is I took the results of these calculations and entered Earth's position relative to the sun in the images and overlaid a circle representing Earth at that same radius in pixels given by the spreadsheet and put that into SAO image DS9. So here's SAO image DS9, and I've loaded the raw FITS files into this program, and we're going to take a look at where the spreadsheet predicts the Earth to be in the image, based again on my orbit, which is not going to be quite as high precision as the official orbit, but it's good enough, and it's good enough to see that the motion is exactly as predicted. So you can see a red circle. This is, of course, the sun, so I've marked the sun's position in the image, It turns out that the radius of the sun in these images works out to be basically 400 pixels exactly. And so the diameter of the sun is 800 pixels. We can see that reflected in the spreadsheet. That's one input on the image. The other input I made for each image was the position of the sun in the image, which is generally right in the center, 512 by 512 in these 1024 by 1024 images. But there were times as the sun was being eclipsed that the tracking starts to drift a bit because it does use the sun for fine guidance. And so I made sure that the red circle stayed centered on the sun for those images so that we get an accurate position on where Earth should be in the image. Earth is represented by a green circle. You can see it's so big relative to the sun from SDO's perspective that it looks basically like a straight line. But this is actually how big Earth is relative to the sun as seen from SDO. It's big. It's really big. And again, this is being predicted by the actual spreadsheet with the calculations from the orbit that I computed using the observations from September 8th. This is the predicted angular radius of Earth, and that's what I've entered into SAO image. So we can now look at this in a time lapse of the eclipse. So I'm going to turn that on now. We can see Earth come in, and then Earth goes out. So again, this green line, this is the edge of the Earth predicted by the orbit that I calculated. And if anything, the orbit that I calculated shows a slightly deeper eclipse than what actually happened, but it's pretty good, considering that I only had one night's observations to go on to calculate that orbit. That accuracy is really not bad. And if you look at the absolute difference in position of my computed orbit compared to the official NASA orbit, they're about 200 kilometers apart. And considering the spacecraft's over 35,000 kilometers in altitude, that's really not bad. And it's good enough to see that this was indeed an eclipse caused by Earth. You can see Earth's atmosphere is expected to cover up most of the sun in these images and then go back out. And it parallels the actual covering of the sun by the Earth's atmosphere perfectly, just perfectly over time. It did come in and then reverse direction and go back out. That's exactly what you can see the green line is predicting should happen. And there's one more thing I want to point out about these images. So you can see this is the original raw FITS file downloaded straight from the Virtual Solar Observatory repository. And you can see that Earth's atmosphere forms this nice smooth gradient, dimming the sun. And this doesn't quite look like what you see on the HelioViewer website. Well, why is that? Well, it's because the HelioViewer website is showing you processed JPEGs that have been contrast enhanced. They're not the raw FITS files. You have to go download the raw FITS files, which are high bit depth images. I've said this many times, but most monitors can only display 8-bit images. These are high bit depth images that have a much wider dynamic range than what your monitor can display. And so to present them on a website like HelioViewer for the general viewing public, they do contrast enhancement and reduce the bit depth down to 8 bits and export them as whatever, PNG files, I think. And that's what you end up seeing on the website, but that doesn't reflect the full dynamic range of the image. And as a result of that, you get what appears to be sort of a jagged appearance of Earth's atmosphere on the edge of the sun. So I've come into Pixen's site here. This is a program I use to process astronomical images, both from my own cameras and from the SDO spacecraft and other spacecraft images as well. And you can see this is what the original raw FITS file looked like before I did anything to it. Nothing done to it at all. This is what it looks like when you try to display it on an 8-bit monitor. It does not work well because an 8-bit monitor can't display the full dynamic range of the image. So you only see the very brightest bits and the details in those bits. You don't see hardly anything else. The image looks, frankly, dark and underexposed, but it's really not. It's just that the dynamic range of the monitor is not capable of showing you everything that's there. The images you saw a minute ago in SAO image are much more akin to what you see here. I've done some histogram stretching here, but I haven't enhanced the contrast so much that it's really blown out. And so I think I used a logarithmic scaling for the histogram on SAO image. Let me check here. Yeah, see, it's logarithmic. If I do linear scaling, we see the same image. We see this really dark image that looks underexposed, but it's really not. So if we change the histogram scaling to a logarithmic scaling, we really see a lot more detail. And this gives us a much nicer view of the image. So that's very similar to what you see here. But if I really crank up the contrast and over crank it, you see this hard edge of what appears to be some sort of dark object blocking the sun, but in a sort of jagged way. And this looks like it's a connected feature of that. I mean, it really looks, frankly, bizarre. And you have this little feature sticking out here. So how can this possibly be the edge of the Earth? How could part of the sun be shining through the Earth? The Earth isn't transparent. You know, that's kind of where a lot of this criticism is coming from. And it's because they're looking at these highly processed JPEGs. This is an over-exaggeration of the situation, but it's the same principle. And so that's why you have to look at the raw FITS file. It's not sufficient to look at HelioViewer and call it a day. If you want to make the claim that this shouldn't be happening, then you have to show me that it shouldn't be happening in the raw FITS file. But that's not what these guys are doing. So the last thing I want to do here is show a graphical explanation for why these eclipse seasons occur, because I think a lot of people misunderstand this or simply don't understand this. And so we're in Celestia here using the orbit that I calculated for SDO from my telescope. You can see the orbital plane of SDO. This is the red line that is going around the Earth, and it is inclined quite a bit by about 28 degrees. And this leads to a situation where SDO will sometimes pass behind the Earth relative to the Sun and be eclipsed by the Earth, but not always, not throughout the year. So here's where we're at right now, September 14th, and we've just left eclipse season, so it's pretty close to being aligned. Oops, I accidentally reselected the wrong thing. There we go. Selecting SDO, you can see the alignment of this orbit almost has it behind the Earth, so that when it passes behind the Earth, it's being blocked from seeing the sun, but not quite. So if we go backwards in time, let's go back to around September 1st in that time frame. Notice that as we go back in time, the sun is moving along the ecliptic, but the orbit of SDO, its orbital plane, is fixed relative to the background stars. So here we go. Oh, September 5th. 4, 3, 2, 1. Great. Okay, so now you can see it's lined up. SDO, when it reaches this part of the orbit, it goes into Earth's shadow. Earth is blocking its view of the sun. The moon's also hanging out there near the sun. Whether an actual eclipse is occurring such that the moon is in front of the sun depends on precisely where you are. And it so happens that SDO was properly positioned to see a double eclipse that day, as we saw in the spreadsheet. But this is just to give you an idea of the three-dimensional relationships at work here. Sorry, I accidentally keep selecting Earth, and every time I do, it shows Earth's orbit instead of SDO's. So you can see that the orbital plane is fixed relative to the background stars. And as we go along in time, the sun will appear to move along the ecliptic. What's really happening is that Earth is orbiting the sun. It's going around the sun in its orbit. And SDO is traveling with Earth in that orbit around the sun. So from SDO's perspective, it's as if the sun is moving along the ecliptic. And as we go further along, you can see there's definitely no situation here. No matter where SDO is in its orbit, it's got a 24-hour view of the sun during this time of year. We're into November, December, So you can see it's got this nice view of the sun. But as we keep going, Earth will end up on the opposite side of the sun from where it is right now. And we'll be back to a situation where SDO's orbit is again aligned such that it will pass behind Earth relative to the sun and go into the Earth's shadow. And this will be happening in about March of next year. I think it might actually start off late February, depending. But this gives you a general idea of what's going to happen. And then a few weeks later, gradually, and I do mean gradually, that alignment will cease. But it takes time. It takes multiple days. If I try to track with it so that the sun stays behind the Earth like this, you can see this alignment is such that over multiple days, you can get an eclipse of the sun caused by Earth as SDO passes behind the Earth. This is going forward in time now. Same story. It takes time. So you see, we're in late February right here, and it's predicted to happen. But this is based on my preliminary determination of the orbit from just a single night's worth of observations. It's good enough to make pretty good predictions about the spatial relationships of these things in the immediate near term, within a week or so of when I conducted that observation. But I wouldn't try to take long-term projections as super precise, but it shows you the spatial relationship of that orbital plane. So you can see how these eclipse seasons come about. It's just a function of basic orbital mechanics, really. So now we're into April. There's definitely no eclipse going on. This orbital plane does not pass into Earth's shadow. No matter where SDO is in this orbit right now, it's got a nice clear view, line of sight to the sun. So I hope that explains everything, and just about an hour from now, we will not be seeing another eclipse of the sun caused by Earth because the eclipse season is now over. So if I'm right about that, if I'm right that eclipse season is now over, and I predicted that successfully, and I predicted the final eclipse of the eclipse season successfully using nothing but just mathematics and the orbit that I calculated for SDO, it begs the question, how could I be wrong about the cause? Because I made a useful, specific prediction about its behavior based on that orbit and based on the fact that it really is Earth covering up the sun. If I'm wrong, fine. There's something else going on. But if I'm right, I await an explanation for how I was able to make such a specific prediction, other than the fact that it really is Earth covering up the sun. Thanks for watching, folks. Clear skies.